so today I'm going to go over the Chapter 3 review questions. As normal, I am not going to go over review question number 1 because that is terms and definitions, and you can use that, you can do that on your own time. Just go ahead before you do the review questions and make your card out, make your note card, make sure you have on it your energy equation, your wavelength and frequency equation. You also need to know the speed of light. You need to know the constant for H. And so go ahead and make that out and try these review questions on your own first, or watch me start it, pause it, try it, and then check it. Don't just watch me do it and do it with me. Like, try it on your own first. That will help you out so much more. Question number 2 is asking for the mass of the average mass of a calcium atom in grams. So you're gonna need your periodic table. So on your periodic table, you're looking for calcium. It is right down here. I don't have it on there, but it's element number 20. And you'll also notice, so if you're looking at your book, you have a calcium. It has a 20 above it, and it's got 40.08. That's a 20. That 20, it looks like this. It's in a square. Means there's 20 protons in every calcium atom. And this is the atomic mass unit. If you'll remember that, that's approximately, it's an average of the mass of, it's the average of the mass of one calcium atom. Now the question is not asking for the atomic mass unit, it's asking in grams. So you're gonna have to remember this conversion factor. And so you're gonna start with 40.08 atomic mass units. And the conversion factor for atomic mass units to grams is 1.66 times 10 to the negative 24 grams per atomic mass unit. So I'm going to put grams on the top and atomic mass units on the bottom. That way AMUs cancel out, and you're going to be left with your answer in grams. When you go ahead, you're going to put this in your calculator. You're going to be multiplying these two numbers. Remember, you need to use parentheses or this will possibly make some mistakes. So go ahead and solve that and come back and check to me. And you should get 6.65 times 10 to the negative 23rd grams. Don't forget what we've learned with significant figures. If you'll come in, you'll look in your problem here. We have 1, 2, 3, 4 significant figures. And then in this one, we have 3 significant figures. So you're gonna therefore report your answer with 3 significant figures. Question 3 is very similar to question 2, except instead of going from atomic mass units to grams, we're actually going in the opposite way. So it tells me I have a specific isotope of nitrogen. If you'll remember, an isotope is still nitrogen and it still has 7 protons, but it could have more or less neutrons in it. That's what makes it an isotope. And it tells me its mass is 2.49 times 10 to the negative 23rd grams. And this time they're asking you to write that in atomic mass units. So when I write this one to convert to atomic mass units, I'm going to put AMUs on the top and grams on the bottom of this conversion factor. So I'm flipping it so that the grams will cancel out. And if you'll remember, the conversion is 1 atomic mass unit is 1.66 times 10 to the negative 24. And when you put this in your calculator, you're going to be doing this like it's a division problem. So you're going to be putting parentheses around this first part, and then you're going to be dividing it by this 1.66 times 10 to the negative 24, and you're going to put parentheses around this too. And we're going to report our answer again with 3 significant figures. I get 15 atomic mass units. There is a second part of this problem. It's asking for me to name or give the symbol for this isotope. So I know it's for nitrogen. And if you'll remember, when you give a symbol for an isotope, you actually have a number up here to the left-hand corner, like the upper left-hand corner right here. And you're going to put in that is the number of protons and the number of neutrons. Now, an atomic mass unit is the approximate weight of either a proton or a neutron. And so since there are 15, that tells me there is a total of 15 atoms in the nucleus of this element. And so I would put 15 and nitrogen. And this is this isotope of nitrogen. Question 4 wants you to say how many protons, how many neutrons, and how many electrons there are in the magnesium-25 isotope. And so you're going to find magnesium in the second column on your periodic table. Mine has the number below it. Yours is going to have a 12 above it because it's the 12th element. But that number tells you, it's going to be right above it in the middle on yours, and that number is telling you the number of protons. So since I have a 12, I know this magnesium is going to have 12 protons. Now, also remember that the number of protons and the number of electrons are the same. The charge balances out. So if I have 12 positive charged items, I need 12 negative charge. Now, the tricky one to figure out is always the neutrons. But I know in this name, it tells me magnesium-25. And that 25 tells me there's 25 particles in the nucleus of this atom. Well, in the nucleus, I've got protons and neutrons. So these combined are going to equal 25. So 25 minus 12, this is going to be 13. There's 13 neutrons in this isotope. Question number 5 has you giving the atomic or the symbol instead of them giving it to you. So they tell you we have an atom and it has 5 protons, 5 neutrons, and 5 electrons. It wants you to give its symbol and also tells you to remember the mass number. So the symbol is going to come from the number of protons because that's what gives it its identity, tells me who it is. So if I have 5 protons, it is going to be the 5th element, and I know that that is going to be boron. So if you look at your periodic table, you're going to have boron with B, and there's a 5 on top of it. That lets you know all atoms with 5 protons are boron. Now it tells you to do the mass number. If you'll remember, the mass number is this number we write up here, and it has the protons and the neutrons, and they make a total of 5. And so therefore for this is 10. We don't include the electrons in this mass number because electrons don't contribute much to the mass. Question number 6 says, what's the most abundant isotope of phosphorus? So if you're going to find phosphorus on your periodic table, below it, it has a 30.97 on that. And if you'll remember to figure out the most abundant one, it's going to be rounding this number to the nearest whole number. So this is going to round to be in 31, and this is the most abundant isotope of phosphorus. I actually tried to give a good example of how that works out on the comprehension check questions. Question number 7 says, what's the most difficult thing to do when it comes to making a nuclear bomb? I actually didn't explain any of this when I was going through the comprehension check questions, but to make a nuclear bomb, you need a specific isotope of an atom. A lot of times it's uranium. It's a specific type of uranium. And so the hardest thing to do when you're making that bomb is to get enough of the right isotope. You can get an abundance of uranium, but it's getting an abundance of just that one type of uranium or of the compound. So it's getting enough of the right isotope is really hard to do. Question number 8 says, what do nuclear power plants use to keep a chain reaction from getting out of control? Nuclear power plants use the same technology that nuclear bombs do. You get this enriched uranium, which is going to be a uranium sample that has a lot of neutrons in it. And it can actually release those neutrons, and it's releasing a lot of energy when it goes through this process. And so what happens in a power plant is you get this type of uranium, and as it's releasing its neutrons, it starts a chain reaction, and it starts releasing lots of these, and they produce a ton of energy. Now, if you're not careful, this chain reaction will get out of control, and you can have a disaster, which we've seen at the Chernobyl power plant, or there's been one in Japan after a tsunami. But to keep these reactions happening at a very controlled pace. They use something called control rods, and it is just a rod that's made up of a substance that's going to be absorbing these extra neutrons to help slow down this chain reaction from happening. Question number 9 asks you to list the colors of light in order of wavelength from longest to shortest. This should come back to you from 3rd grade science. Hopefully, if you ever studied Mr. White Light with Roy G. Biv. I'm not gonna write all the words out, but I will write Roy G. Biv out for you. And so it's red, orange, yellow, green, blue, indigo, and violet. And if you'll remember these indigo and violet lights, these have these shortest wavelengths, which means the waves come really close together. They bring a lot of energy, and that is how you have gets close, like your spectrum of UV light, and that can cause a lot of damage to your skin. Question 10 tells me light has a wavelength of 231 nanometers, and it's asking you to convert it to meters. Remember, you can't use King Herod diode for this. You have to remember the conversion unit. So I'm going to meters, so I'm going to put meters on top, and I want nanometers to cancel out, so I am going to put it on the bottom. And the unit is that 1 nanometer is 1/10 to the -9th meter. So nanometers will cancel out, and you shouldn't have to put this in your calculator. You should just be able to see that it will become 2.31 times 10 to the -7th meters. Now, why didn't I just say 231 times 10 to the -9th? Well, because when you write it in scientific notation, you have to move that decimal over twice, making it go from a -9th to a -7. Question 11 is a continuation from question 10. It's asking you, what's the frequency of the light in the previous problem? And so for frequency, we're going to use when we had converted it from nanometers to meters, because if you'll remember, our frequency equation is F equals C over lambda. We're looking for F. C is that constant. That's the speed of light in air, and it's actually given to you in meters. So since it's given to you in meters, you have to make sure when you put in the wavelength that you put in the wavelength in meters too. And so when you put this in, make sure you're using parentheses on the top and the bottom. Meters is going to cancel out, and you're going to end up with a frequency. You get a frequency of 1.30 times 10 to the 15th per second. Per second is a hertz, which is a measurement for frequency, so you could also put a hertz there as your unit. Remember, you've got 3 significant figures in all your data going into the problem, so you need 3 significant figures in your answer. Question 12 is also using the frequency and wavelength equation. It tells you light has a frequency of 3.45 times 10 to the 17th hertz, and it's asking you to convert it to wavelengths. So we're gonna once again use the frequency is equal to C over wavelengths, and they gave me the frequency, so I'm gonna put it in for F. I'm gonna go ahead and convert that hertz to the 1/2, that is its unit. And I know C, and if you don't know C, you should learn it at this. And I am looking for the wavelength. So to solve for wavelength, I would multiply both sides by lambda. And then to get lambda alone, I'm going to divide by this. So now you're going to put this into your calculator. These seconds are going to cancel out, and you're going to be left with meters, which is a wavelength. Now, make sure you remember those parentheses on the top and on the bottom. And once again, both our numbers have 3 significant figures, so try to get your answer to have 3 significant figures. I'm going to leave this in meters because it doesn't say I have to convert it to nanometers. Question 13 asks, what does the term electromagnetic waves refer to? And as you study later on in physics, you'll actually study a light wave. This is made of two parts. It's made of what looks like an electric wave and a magnetic wave. And so we use the term electromagnetic wave to refer to all light. So this is like the light spectrum, not just visible light. It even contains light that you cannot see. Question number 14 asks you to name 3 categories of electromagnetic waves that are not visible light. And so we have a bunch. We have gamma rays, which gamma rays are actually used in a medical procedure called Gamma Knife to help treat some tumors. We have X-rays, which if anyone has ever broken a leg or something, thought you did, you had to go to the hospital, get an X-ray. We have UV, shortened for ultraviolet light. Those are those rays that come off of the sun that are very damaging to your skin. You have IR, or infrared light. This is actually the light that your remote control uses to turn on your television. And you have, there's a bunch, but we have microwaves. I hope you know we use those to cook your food, or you probably cook your food. And we have radio waves. These are really long waves that carry radio signals long distances. So there's lots of types of waves on the electromagnetic spectrum other than the visible light. There's actually way more that you cannot see than there is that you can see. Question 15 tells me that a photon, which is a packet of light released from an atom, has a frequency of 1.94 times 10 to the 16 hertz. And it's wanting to know its energy. So you have to remember the energy formula is E equals H times F. And I'm looking for its E. And H is that constant, that Planck's constant that you need to at least have written down somewhere. And so as you have your Planck's constant and you've written it on your note card, please remember to write down the units. As I check my students' work, I am checking the numbers, but I'm also looking for units. It's an important part of the problem. And you're gonna then continue on with your frequency. I'm gonna write hertz as 1/2. That way my units can cancel out. And I'm just gonna multiply these. As you multiply seconds on the top and seconds on the bottom, it's gonna cancel out. And you're gonna be left with joules. Now remember, parentheses. I know I say that all the time, but all the time, joule, use parentheses. So energy is gonna be in joules. And we have 3 significant figures in each of these, so your answer is gonna be reported with 3 significant figures. And you get 1.29 times 10 to the negative 17 joules. Question 16 is similar. We're still using the energy equation. It's telling me a photon and it has an energy. It's giving me the joules this time, and it's wanting you to find the frequency. So you're still gonna use this Planck's constant equation, except this time I know the energy. And I'm looking for the frequency. So when I put in Planck's constant, to get F alone, I am going to be dividing both sides by 6.63. So go ahead and put it in your calculator. Remember those parentheses, and we're once again going to report our answer with 3 significant figures. It's 1.79 times 10 to the 17th. 1/2, or you could make the unit be a hertz. Question 17 tells you that orange light has a wavelength of 612 nanometers, and it's wanting to know what energy does the photon have of this light. Well, like we've just done the energy equation a lot, for the energy equation, we need to know the frequency, but they didn't give me the frequency, they gave me the wavelength. So the first part of the problem is going to be going from wavelength to frequency. And we're going to use the frequency equals speed of light over wavelength. So I don't know F. Go ahead and put in the speed of light. And they gave us the wavelength, But if you'll remember in this for the wavelength, since the speed of light is in meters and they gave it to us in nanometers, we actually have to go from nanometers to meters. So there's 3 steps to this problem. So I'm going to come over here and squeeze it in. And so you're going to say 612 nanometers times 10 to the negative 9th over 1 nanometer, and that will give you your answer in meters because nanometers is going to be canceling out, and so you get 6.12 times 10 to the negative 7th meters. So this is going to be your wavelength. Now, meters is going to cancel out, and you're going to be doing the division. Remember your parentheses, and since you have 3 significant figures, your answer is going to have 3 significant figures. And so when you've done the division for this one, you're going to get that the frequency is 4.9 times 10 to the 14th per second. So we're going to take frequency, and we're going to put it now in this energy equation. I am looking for energy. H is Planck's constant, and you get energy as 3.25 times 10 to the negative 19th joules. Now there's 3 parts to that problem, so I'm just going to go ahead and recap it. It gives you light wavelength, and it's wanting you to find energy. It gives you the wavelength in nanometers, and in order to find energy, we have to know frequency. So we have to use the frequency equation. But to use the frequency equation, we have to have it in meters. So the first step, I took the wavelength and I converted it to meters. I then was able to take the wavelength and use the frequency is C over wavelength formula to get a frequency. But once you have a frequency, you can use the Planck's equation and you can get an energy in joules. Question 18 says a photon, and it gives me the energy of 2.17 times 10 to the negative 18th joules, and it's wanting me to find its wavelength. Well, I know from energy, I can't find wavelength, but I can find its frequency. So the first part is you're going to find your frequency. So when I use Planck's constants equation to find frequency, I'm putting in what they gave me for energy, which is 2.17 times 10 to the negative 18th joules. I'm putting in Planck's constant for H times the F for frequency. So I'm going to divide both sides by this number. And when I divide them, the joules is going to be canceling out. Remember those parentheses that I keep reminding you about. And you're going to be getting a frequency of 3.27 times 10 to the 15th. This is like per second. And that's your frequency. Now the question doesn't ask me for frequency, it asks me for wavelength. But we're used to this equation now. Frequency equals speed of light over the wavelength. So you're just going to take this information, right? So when I put in for frequency, I put in my 3.27 times 10 to the 15th. I'm going to erase this for space sake. And you have your speed of light and your lambda. So I'm going to multiply both sides by lambda to get that. And now to get the lambda alone over here, I'm going to divide both sides by the 3.27. And you get your wavelength as being equal to 9.17 times 10 to the negative 8 meters. So this equation, I'll just go over it again, gave me a photon's energy in joules, and it wanted me to calculate the wavelength. Using the energy equation, I can't calculate wavelength, but I can calculate the frequency. So that's what I did first, is I calculated the frequency. And once I had the frequency, I put it into the frequency equation to then calculate the wavelength. So question number 19 is another electron jumping orbitals and a hydrogen atom. It tells me that I have a hydrogen atom and it's in N5. And so I have an electron and it's come out to N5. And as it goes from N5 back down to its ground state, it releases a wavelength with a 95 nanometer wavelength of light. And so the question then asked, if I had another electron and I wanted to jump it out to N5, how much would it have to, like what wavelength of light would it have to absorb? Well, if it released when it came back 95 nanometers to get back out there, it would have to absorb light with a wavelength of 95 nanometers. Question number 20 is another electron jumping orbitals question. It tells me the electron of a hydrogen atom goes from the N3 to the N1 orbit, and then another one goes from N2 to N1, or its ground state, which is N1. Which electron released a photon longer in wavelength or higher in frequency? So the two things we're looking for is long wavelength and a higher frequency. So in order for a photon to go from N3 to N1, it had to absorb a lot of energy and had to let it go. And the same for this one, but to go from N3 to N1 is 2 steps. And from, like, you're going out 2 energy levels and back in, where this one is only 1. So it takes more energy for the electron to go from 1 to 3 and back. So this electron is going to have a higher energy. Now, if you'll remember, if we look at our energy, if we use our energy equals HF equation, as energy goes up, the frequency is going to be going up. And so, since this one has a higher energy, it's also going to have a higher frequency to go with its higher energy. Now, this one has a lower energy because it's not having to take as many steps. With its lower energy, it has a lower frequency. Though, if you will remember, a lower frequency is a larger or a longer wavelength. So this one is going to have the longer wavelength. These problems that we keep seeing, they're wanting to make sure that you understand that frequency and energy are directly proportional. As one goes up, the other goes up. And they're also wanting you to understand that frequency and wavelength are inversely proportional. As one goes up, the other goes down. All right, so as we're doing these for question 21, is asking us, what is an assumption that this model is making? So as we use this model called the Bohr model of an atom, and we're analyzing how electrons go up and down, we are making the assumption that electrons cannot be in between an orbital. We're assuming that they have to go from like one step to the next and they can't be found anywhere in between. And so the question is just asking you, what's the assumption? The assumption is that electrons are restricted to certain orbitals and that they cannot be in between. Number 22 is kind of a really interesting thing to think about, but atoms are more than 99.999% empty space, which is really kind of weird if you think about it. But when you have an atom, you have stuff in the middle, but when you have this orbital, it's all empty space except for like the one spot where the electron is located. For question 23, I will add pictures of the spectrum below, but it gives you pictures of a spectrum for several different compounds. And by spectrum, I mean a light spectrum. If you were to take these compounds and you were to do a flame test on them and look at them through a device that allows you to see what light they're emitting. So it tells you a spectrum for hydrogen and helium, lithium, sodium, quite a few. Then it gives you a sample that I'm going to add up above. And from the sample, you're going to compare it to the hydrogen, lithium, sodium, potassium, strontium, and barium and see what you think is in the sample that you have. So if you look at the one that they gave you, you're going to see on it a red band towards the far right of it. And so that red band towards the far right, and then you're going to see a lot of purple towards the left. And so the only element that matches up with those features is hydrogen. Hydrogen has those purple and that red. The other one that you're gonna see is, look at lithium. You see a bright orange and a red band, and those bands are on your spectrum. And so the two things are, oops, I misspelled hydrogen, and lithium. Good job on the chapter 3 review questions.